All right, good morning, ladies and gentlemen, and welcome back to AP review of springs and simple harmonic motion. Spring basics. Stress is the force applied to a spring. Strain is the change of the length. These are the important ones. The equilibrium is the unstrained position. Restoring force is always seeking to restore equilibrium.
Yep.
Okay, you guys have these already. Hooke's law, the restoring force of a spring is proportional to its displacement from equilibrium, ideally.
It's like when you stretch a rubber band. The farther you stretch that sucker, the harder it pulls back.
And this doesn't really help us at all, so we have to put that constant in there, our spring constant, where K is a spring constant for that spring, and there's a relationship here. The spring constant is the relationship between the force of the spring divided by the...
How far you stretch it.
Okay, the work done moving a spring is stored in the spring as potential energy. And I'm gonna go ahead and just write this down. I'm gonna write it down right here because I don't have a lot of space.
Oh yeah.
1/2. Okay, this is just like 1/2 mv squared, right? It's very similar to. It looks. It's not the same thing, but it always reminds me of it.
The calculus it ends up with a similar result, but don't think of it as the same.
The law of conservation of mechanical energy now has a new member. Okay, so we used to think about the energy total in two ways. We used to think it was the kinetic energy plus the UG, and those are still legit, but we're going to call this translational. And then we also, this is after we talked about the rotational unit, so the kinetic energy rotational, plus we also have the UG of the spring.
USP.
The USP. Okay, it's not really the UG, it's the potential energy of the spring.
Yeah, U is potential energy.
Okay, so a practice problem. An archer pulls a bowstring back 0.47 meters before releasing an arrow.
So the delta X is 0.47 meters. And the spring constant is 425 newtons per meter.
Okay.
Oh, if he pulled it back a full meter, that'd be 425 newtons, but he's not pulling it back a full meter. It's a little less than half of that.
Oh, okay.
So,
what is the elastic potential energy of the drawn bow? So it looks like when we're talking about the potential energy, we're talking about
the energy that's stored in that bow.
So our USP is going to be 1/2 kx squared, 1/2 k for 25 Newton meters times k. Wait, 1/2 k
X squared.
X, there we go. Okay. It's hard to look at this board right now. Is it colorful, Mr. Boykin?
It's colorful.
Dang it. Sorry, guys.
Oh no, but this is not. No,
Okay, good. All right, put those right there. Stay. Okay, so 0.5 times 425 times 0.47 squared, and I get we're gonna call it 47. Okay, 47, and
that's
my units.
Newtons. I beg your pardon, joules.
Oh, because these are squared, right? A Newton meter.
Yep.
Joules.
So you've got 47 joules stored in the bow.
Okay, on to the next. If the arrow has a mass of 0.03 kilograms, what is the speed of the arrow as it leaves the bow?
Well, what happens to the energy stored in the bow when you let go of it?
Well, okay, so work changes energy, and that USP is going to get changed into kinetic energy.
That's right. And kinetic energy is 1/2 mv squared.
Okay, so whatever our USP is, it's going to be equal to our kinetic energy, which is 1/2 mv squared. So we could just take that number right there, 47 joules.
Times 2.
You know, let me do the math here first before I plug in numbers. Okay, so I'm gonna multiply it times 2, divide by m, and I'm gonna take the square root.
That's it.
Right? Okay, so running out of space here. So square root of 2 times the kinetic energy, which we said is the same thing as the
47
USP.
joules.
Okay, divided by the mass, which was 0.303, I'm sorry, kilograms. Okay, and then we should get our answer there.
You know, it occurs to me that they should be doing this.
They should be doing it. I hope they're doing it. Without me?
Yeah.
Do I need to be doing this with them? Maybe we'll pause after this one. 2 times 47 divided by 0.03.
Yeah.
And I get 56.
56 meters per second. That's pretty fast. Arrows are dangerous.
Okay, so Mr. Boykin's got a good... I don't even know if there's any other practice problems after this one. There might be 1 or 2.
Let's find out. I love a surprise.
Woohoo! Okay, so if a spring is strained from equilibrium and released, it will oscillate back and forth.
Like this.
You got it? Look at the little cutie. Come on. Yeah. So cute. Okay.
We did this. I remember this.
Yeah. Miss Moore struggled to make it go up and down and not side to side. Okay, so this simple harmonic motion has a period and a frequency to its oscillation.
The period is the time it takes to go up and down.
1 cycle.
And oh, sorry.
The period is the time for 1 cycle, which Mr. Boykin just showed us. What the heck is frequency? Well, the number of cycles in 1 second. That's a pretty slow frequency over there. Okay. And there's an inverse relationship here, right?
Yep.
Units. So for period, it's seconds per cycle. For frequency, it's cycles per second.
Heights.
Heights. We like cycles per second, but hey. Okay, amplitude is the maximum displacement from equilibrium the spring moves. And its frequency is unaffected by its amplitude. It doesn't matter how, how much you pull it, how much force you pull it with, the frequency is still going to be the same.
This is a rather small amplitude. Equilibrium is somewhere about there.
Mm-hmm.
Okay, and if I give it a larger amplitude, that's a larger distance up from equilibrium and down from equilibrium, but the frequency is the same as when it was
I wonder why that is.
barely moving.
Okay, a ball moving around the unit circle moves with an angular speed of omega, where omega is equal to 2 pi over t.
And that's basically distance over time.
Yeah, v equals distance over time.
But then we're measuring distance in radians per second. You guys remember that video where we showed the ball going around the circle?
I thought it was really helpful. The ball goes around a circle, and then the shadow of the ball exhibits simple harmonic motion.
Yeah.
Right? Where the omega is called the angular frequency. And so this is the equation that we just saw. And then we know that the period is the inverse of the frequency. So instead of 1 over t, we just call it f for frequency.
Yeah.
Okay, so this equation is going to be on your AP equation sheet. How do we use it? What is it? Starting from x max, the position of the shadow on the x-axis depends on the amplitude, the angular velocity, and time.
Yeah.
So position depends on these things right here.
Yeah.
And we didn't really do much practice with this, and it's always a gamble to try and figure out if stuff's going to be on the AP exam, but there it is, and that equation will be on your sheet. Now here's that exact one we just saw on the previous slide, and I've taken omega and we have added in 2 pi frequency because you can substitute that. It's equal to that.
And we did this back in when we ran through it the first time.
Yeah, just a few practice problems. Okay, so what happens to the velocity of the mass on a spring as it oscillates?
That's a good question.
Well, it changes, right? Right, so
That thing is not moving hardly at all. But
it's not moving right now, but so we get it moving. What is going on with the velocity? Well, my first
What
question,
happens at the bottom?
Well, at the bottom, it has to stop and change directions.
Yeah, and what happens at the top?
Well, the same thing. And what's going on in the middle? Okay. So we're gonna come back to that. Starting with at time when t equals 0, at equilibrium, the velocity at time t, if you wanted to figure out the velocity, you could use this equation.
Yeah.
So V max happens, and this was the question that Mr. Boykin and I were just talking about. V max occurs as the mass passes the equilibrium point. Okay. V. So we said at the top, right? And we'll see this. At the top and the bottom, the velocity is 0, right?
Yep.
But it's the max at the equilibrium point. And so
Let's say here it is at the top on the way down. It's going fast. Gravity is causing it to accelerate it until it gets to equilibrium, and when it goes past that, now the spring's pulling it up. So the spring pulls it up, it goes faster and faster until it gets to equilibrium, and then gravity slows it down. So the maximum velocity is right at equilibrium.
Yep, that makes sense. Why is this the fastest point? We just talked about
I think
that.
it's time to go to the diagrams over here, or should we do that later?
Six on my thing.
Yep, we got to do this.
Yeah, okay.
So here's equilibrium, here's time going by, here's up, and here's down.
The
So
top and the bottom,
as it passes equilibrium, it goes to the top, and then it comes back to equilibrium to the bottom, and then back to
Yeah,
equilibrium.
it's just oscillating, right? Up and down, up
Yeah.
and down. Okay.
And so what happens to the force?
I think that's my next slide here. Yeah, what happens to the restoring force as the mass oscillates, right?
Well, the force is equal to negative kx.
Okay, so that's like saying the force is exactly equal to the x, but just like the opposite, right?
Yeah.
So if this is the top and this is the bottom, as our spring is moving, oscillating towards the top, what we're having is a force in the negative direction pulling it
Trying
down,
to put
right?
it back to equilibrium.
That's what we have here. We have this is the negative direction, our force being negative here.
And then when it passes through equilibrium, the force goes to 0.
Yeah, now our spring's at the bottom here.
Well, as it passes through equilibrium, the
sorry.
force goes to 0.
Oh yeah.
And
right,
now,
right.
as it goes down,
Okay. Oh, trash can. Okay. So once it passes through equilibrium, the force there is 0, right?
Yeah.
There's no restoring force pulling it either way. And now when it's at the top, now when it's at the bottom, now it's being pulled in the positive direction, right? Back up. And that's why we've got a positive force here. And then back to 0 at equilibrium.
and the question before was what happens to the velocity? Well, where is it going the fastest? At equilibrium.
At equilibrium. Yeah. And so if you want to look at, our slope over here, this is our velocity versus time graph. And you can see that at time 0, it's going the fastest. Why is that? Let's take a look at
on
our,
its way. Okay, yeah, the fastest slope.
and then it's 0. So this is a position versus time graph. Not to say the derivative, but
Yeah.
the
Slope.
the slope of the line is going to be the velocity. It's 0 at 1.
At 1.
We've got 0 here, and then at 2 seconds, we're going fast again. Okay, but
And that's
negative.
in the negative direction, negative
Okay.
slope.
And then here, 0 again. Okay, 0 right here, and then again, and then right here, we're going fast again.
So what do you got? This looks like the sine on
The
the left and
max.
cosine on the right. Is that it? I can't remember.
Yeah, it's been a while since I calculus. Okay, so what happens to the restoring force as the mass oscillates? We already answered this question. It's basically changing with respect to the location. The restoring force can be the most at the bottom and the top, pulling it back to equilibrium. Where would the restoring force be the greatest and the least? We just said greatest at the top and the bottom, least in the middle. There's no restoring force acting.
It's trying to restore equilibrium.
Yeah, at equilibrium, there's no force restoring it because it's already at equilibrium. Okay, what about the acceleration of the mass as it oscillates? Okay, acceleration is force equals mass times acceleration, right?
So,
It's gonna be the same as our force here, right? And that's all there is to it. Okay? Is accelerating the most at the top?
and we
and the
spent
bottom?
time talking about this when we went through this originally.
Yeah. Okay, so starting with time equals 0 at equilibrium, the acceleration at time t, if you wanted to figure out acceleration, here it is.
Yeah.
What determines how fast the spring went up and down? Why? I remember when we shot this video originally, we had 2 different setup here.
We had a silver spring and a gray spring.
Yeah, and so those springs were different, which means we have different spring constants. And then we had a 50 gram and then I think maybe 100 grams.
Different
on the other
amounts
one.
of mass on there.
Yeah, and so the 2 things that affect determine how fast it goes, the velocity of our angular velocity here are going to be our spring constant and our mass.
Yeah.
For a spring oscillating with some amount of motion.
It's very likely that you'll get this equation.
Yeah.
And you'll come across this in the AP test.
I apologize. I said our angular velocity, but this is the frequency.
Yeah, angular frequency. It also stands for angular velocity for other things.
So here's our angular frequency, which is equal to the square root of our spring constant over the mass, which is also equal to the 2 pi over t, which is the same thing as our 2 pi over f. I'm going to erase this book, and I'm going to write those on the board because they're going to be helpful for us. My throat is kind of itchy right now. Okay, so I've got angular frequency is equal to the square root. Okay, which equals over t, which equals like that. Okay, use the data for the period. If you're looking for some homework, you can do this. Use the data for the period of oscillation from the spring lab that we did a while back to find the spring constant.
Yeah, we could measure, up and down 10 times. 1, 2, 3, 4. We measure how much time, divide that by 10. That is give us the period. And once we had the period, we know the mass, we could solve for the spring constant.
Yeah, and I think we also...
You'd have to square everything.
Yeah. Look back at your lab there, and if you want to take on that challenge, just review yourself, take a look at it.
Yeah.
Okay, a simple pendulum also shows simple harmonic motion. Oh, look at it. So cute. That's a big pendulum. Okay. The frequency of a pendulum depends on the length and the acceleration due to gravity. So
here we've got this big long thing that's at least 3 meters, and it's got this period. Back and forth, back and forth. Okay, but if you stop it, I'm at back and forth and back and forth. So you change the length, that changed the period of the pendulum.
And of course gravity's at play here,
If
right?
we were on the moon, the force of gravity is what's causing this thing to work.
And just like with the spring, the amplitude does not matter. So if I go, back and forth versus back and forth, right? It doesn't really, the amplitude does not affect the frequency.
Correct.
And here's our equation. So for small amplitudes, the angular frequency is equal to, this, okay, which equals the square root, and we said it depends on the gravity, the force of gravity, and the length.
Yep.
Okay, so there's lots of things that are equal to each other here. So for a pendulum...
They should do this. We're not going to do this.
Yeah, do this. So for a pendulum of length 1 meter, so you've got the length right here. You want to find the t. Okay, so what could you set equal to each other here in order to figure that out? We have certain things, okay?
No, that's a spring up there on the top. Don't be...
Oh, sorry, this is for
Keep
the
it with the
pendulum.
green.
Pendulum and spring, okay? Ooh, get rid of that, okay? So looking over here, do we have, what do we have here?
This is also equal to 2 pi over t.
Yeah, or equals, that's what I was looking at there. 2 pi over t, okay? So it says for a pendulum of that length, find the angular velocity.
Omega, and then solve for either frequency or period.
Exactly, absolutely. Okay.
And you can do this. And I think that's it.
There's one more here.
Oh.
How long must a pendulum be to have a time of 1 second? So what are we solving for this time here?
Period.
Sorry, not a time, a period. Okay, so we're talking about a pendulum for a period, and we
We're given the period, and we want the length.
So we want the length that time.
Yeah.
Okay. Okay.
So just solve that equation for length.
You can do it.